after this lecture because due date is today. So that solution is very easy.
You just said
you will need that.
The exam's going to be next Friday, not this Friday, but next
I'm
Friday. It's going to be over homework 3 and 4.
For National Congress of so-called Material Research 2016. I'm not going to be on campus. So I'm not sure I can give homework 4 back to you or not. But I'm going to post the typed solution on the BP system. You can use it as a reference if I cannot get it back. Hope I should be able to get it back because whole week the grader should be able to finish the grading. Okay? And if you have questions about the exam, you can email me. I will try my best because I cannot type equations on my laptop. Maybe I can use my laptop, but iPad or iPhone, I cannot do that. Okay? So I will try my best to get back to you as soon as possible if you have questions on the exam. And I'm going to do a review this Friday, so please be here. I'm going to do a review covering what is going to be tested in exam 2. Okay? Basically, it's homework 3 and homework 4. It's shear flow and direct stress, something like that. What you have done in homework 3. I already set the exam problems actually because I was planning to do the exam on Monday. So I already set the exam problems. And when you are looking the exam paper, the first page, the exam date is still the old date. So it's a Monday, but just forget about that. Okay. First one is about skin stick model shear flow, something like that. Shear flow. What you have done in homework 3. Direct stress on bone area, shear flow in the skin. This is the first one. Second one is going to be composites. So this is basically what we have covered after exam 1, right? We learned something about direct stress on bone area, and we also learned something on composites. So please be sure and please tell your friends to be here on Friday. Okay? I'm going to do a review. And another thing about the final project. Maybe by this Friday, I can ask Chris to post the final project. We are trying to make it as a mini project to reduce the difficulty because in the past years, this course are doing a very complicated wing structure analysis, the whole wing structure. That is for a group project. But in this class, I put project. Okay. Some students have internship off campus, and in the company they have their own project to work on. In that case, you can propose what you have done to me, what you are going to do to me, what is the objective, what is the motivation, what is the goal for this project. You can write a white paper to me, I can approve it. If you want to do your own project, using ANSYS. So I'm going to assign a mini project. But if you insist, I'm going to do my own project because I'm doing this for my internship, I'm doing this for my future career, but you have to propose this to me very clearly. What is the motivation? What is the geometry? What is the expected outcome? That will be fine. How about that? Okay? Actually, that is a good idea because that will give you a smooth connection from what you have learned in this class to our future career. Okay. I'm going to continue introduce the analytical analysis of buckling of structure. Buckling is a kind of failure mode. When you apply a compressive loading on a structure, sometimes the structure becomes unstable suddenly. And what is that critical compressive loading? This is basically the objective of buckling analysis of structure. We're trying to figure out this key. What is the critical compressive loading to make this column to be unstable? And we derived from the balance equation, force balance and moment balance. Okay? We derived this. We do the first step is to plot a free body diagram, and then do moment balance and force balance, and then you can get the governing equation. The governing equation is at here. This one. So this omega or W. This is called W. The displacement along z direction. Okay. So this is the deflection. The deflection of the beam is governed by this equation, and the Young modulus and the area moment of inertia is I, and P is the critical loading. So we are trying to use this equation to determine what is P to have buckling for the structure. And then we define a constant, k squared equals to this one. The coefficient will be rewritten as a k squared. So last time I got a question asking what is k. This is k. We define k like this way. K is a function of Young modulus, area moment of inertia, and the critical and the loading, the compressive loading. Okay. When you define t like this way, you can rewrite this equation. And this is a very general equation for the ordinary differential equation. You can check any mathematical calculus textbook. You can find the general solution for this equation. This is a general solution for this equation. The solution will contain 4 coefficients, C1 until C4. These 4 unknowns will be determined by the boundary condition, by the boundary conditions. So what is the boundary condition? Boundary condition will be depend on what is the structure you are doing. Pin beams, or fixed free end, or fixed pin. So this is the first example I did. 2 ends are constrained by the pin joints. And then the solution is general. The boundary condition for this one will be specific because you are using 2 pinning joints to constrain the 2 ends. So the deflection, of course, will be 0. And because it's pinning joints, the moment will be 0. The moment will be related with the second derivative of the deflection. So this is 4 boundary conditions. You have 4 unknowns, you have 4 boundary conditions. You can determine what is the equation for you to use to determine this C1 until C4. This is the equation I ended with last time. When you use that 4 boundary conditions in the general solution, the first line is the general solution, and then you use that 4 boundary condition, you will get 4 equations. This is the equation you have. You want to make this solution to be non-trivial. So-called trivial solution is C1 until C4. All of them are 0. If all of them are 0, the deflection will be 0. This is so-called a trivial solution. Does not make sense. It's not important because that means there's no any deflection. You do not have to worry about that. For these 4 equations to have a non-trivial equation, the coefficients. A, you can imagine this is A, this is B. A times B equal to 0. B cannot be 0, so A has to be 0. Right? This is a mechanism how we figure out what is K. So this one, the coefficients has to be 0. Determinant of this coefficient matrix has to be 0. And then what is next? This is a 4x4 matrix. If we want to calculate the determinant of this 4x4 matrix, it's not that straightforward. It will take a while. So we need to reduce the dimension. According to the first line times the first column, what do you get? C2 will be 0. Right? First row times the first column, you get C2 equal to 0. Right? And then you use the second. Do you want me to? There's a 0 here, sorry. So the first row, I made a typo last time. The first row should be 0, 1, 0, 1, not 0, 1, 0, 0. So if you use the first row times the first column, you will get C2 plus C4 equal to 0. And if you use the second row times the column, you will get C2 equal to 0. Right? K squared times C2 equal to 0. K is not 0, so C2 is 0. From these 2 equations, you can get C4 is 0. So immediately, C2 and C4 are actually 0. So you can reduce this 4x4 equations to a 2x2 equations. I do not have to worry about C2 and C4 anymore. So that equation will be reduced to sine KL L minus K sine KL minus K square cosine KL.
I summarized what he said at the beginning of this video.
Cosine KL
It's just
zero.
what I told you now.
So
I'm keeping,
when's the review? Next Wednesday?
because C2 and C4 are 0,
This Friday.
I'm going to
Exam
only
next
use
Friday.
these four numbers. Right? All of the coefficients related with C1 and C3 should be there. So the reduced 2x2 matrix should be this one. Sine KL L K square sine KL 0 times C1 C3 equal to 0. I get this equation through using C2 and C4 0. You only have two unknowns, C1 and C3. And then this coefficients has to be 0 because C1 and C3 cannot be 0. If C1 and C3 are 0, everything will be 0. So the coefficients of this one is 0 means determinant of this one. If you note this equation, note this matrix as A, determinant of this matrix is 0. This is a 2x2 matrix. The determinant is very easy to get it, right? Just this times this one minus this one times this one. This is 0. So you will get K square L sine KL equal to 0. And then what is next? K squared is defined as EI divided by P. It's not 0. Young modulus times area movement inertia divided by loading. L is the length. It's not 0. So these two are not 0. Put them together is 0. You have to have sine KL equals to 0. So from this, you can get sine KL equal to 0. And immediately, you can get KL equals to n pi. Right? N could be any integer, 1, 1, 2, 3, any integer. This is the final solution we have. KL equals to n pi. It's a function of pi, but it's a finite number. So from this, you can derive K equals to n pi divided by L. And then K squared equals to n squared pi squared divided by L squared. Right? But from the very beginning, you already defined K squared. It's EI divided by P. Right? So this is a definition. Before you do the derivation, this is a solution right now you have. So this one must be equal to this one. Then you can figure out what is P. Our objective is to figure out what is P. Right? So from these two equations, you can figure out, okay, EI P equals to n squared pi squared L squared. And then what is P? P will be I made a mistake. This is P divided by EI. Sorry.
Number 8.
EI divided by P divided by EI. I have many tables in my notes. So K squared is defined as P divided by EI from the beginning, not EI divided by P. Okay. So if you have that, that means P will be, if you use P EI equals to n squared pi squared divided by L squared. From this, you can derive P will be n squared pi squared EI divided by L squared. So this is a compressive loading we are trying to calculate. When the structure, right now the structure is very simple, it's beam. When the beam, we have buckling. So it is a function of n. All of the other things are constants. Length, Young modulus, area movement inertia. So it is a function of n. N from 0 to 1, 2, 3 until n, until a very large number. So what is the minimum critical loading?
I forgot to print this one off.
What is the minimum critical loading? N equals to 1. Right? N equals to 0 does not make sense. That means we do not apply any loading. So N equals to 1. This is the so-called critical buckling loading. Pi square EI L square.
Yeah, that's what I got too.
And I couldn't.
Okay. This is a critical buckling loading for this beam structure. And when you have this, what is next? If this is a loading, what is a deformed shape? What is a deformed shape? If we want to look at what is a deformed shape, we have to go back to check what is the function for the deflection. So that one is sine kx plus, because C2 and C4 are already 0, we have 4 terms at the beginning. After we use boundary condition, C2 and C4 are gone. We only have C1 and C3. This is the term associated with C1, and we have another term. So this is a deflection function, right? And the boundary condition for the pinning beam, two ends are pinning joints. So at the right end, when x equals to L, there's no any deflection. This is one of the boundary conditions, right? So if you use this boundary condition, sine TL plus C3 L equal to 0, and then from this you can derive C3 equals to C1 sine TL. What is this? Sine TL. What is sine TL? What is TL? TL is there. TL equals to n pi, right? So sine TL will be 0. That means C3 can be 0. Right? We go back to check. The boundary condition we can further reduce the unknown. We can only maintain only one unknown. C2, C4 are 0. And from this derivation we found C3 is also 0. So the only unknown will be C1. Okay? So this is a function for the deformed shape. Can we determine C1 from all of the boundary conditions that we have? Just a common imagine, if buckling happens, can we determine what is the magnitude of the buckling? You compress over a beam and increase the loading, suddenly the structure becomes unstable. This W is a deflection. Can you predict what is that deflection magnitude when buckling happens? Basically, you cannot, because that is mathematically that is unstable condition, can be infinite. You compress over something, just like a soda can, you just punch it. And you don't know what is the buckling mode will be, but you know the shape. You don't know what is the magnitude of that buckling. C1 is the magnitude of that buckling, but you will know the shape. What is the shape? It's following a sine function. C1 is a constant, but the shape is following this. Sine kx. Sine kx is a function of x. So you can predict the shape, but you cannot predict the magnitude. This is a so-called instability or failure mode. Any failure happens, you will not know what is going to happen after this failure. Fracture, plasticity. When plasticity happens, plasticity means permanent deformation. You increase the loading, suddenly the structure begins, the materials begins to flow like a liquid. So you don't know what is the deformed shape after that yielding point. That is so-called failure. Buckling the same thing. You increase the load, suddenly it becomes unstable. We can predict the shape, but we cannot predict the magnitude. Okay? So C1 is the magnitude. Sine kx is the shape. What is the shape? If n equals to 1,
like a distributed load that
then
was changing as a triangular load. What I did is I made it uniform, and then I
PCR equals to
the extra would have been.
pi
And then
square
I put it all at
EI
one point on the bigger side.
L square. This is a minimum critical loading. And at this point, K square equals to, we derive K,
it wouldn't work as a triangular equation.
we derive the K at here. K square equals to N square pi square L square, right? So when N equals to 1, this equals to pi square L square, right? From this, you can get K equals to pi over L. And then you go give this K back to the equation for the deflection. Wx will be C1 sine pi x L. This is the deformed shape. This is the constant. Forget about it. Magnitude. We don't know what is that. But this is the shape. So what is the shape? You can plot it. One end is pinning joints. Another end is also a pinning joint. This is PCR when n equals to 1. This is PCR equals to 1. And the deformed shape is following a function C1 sine pi x equals to L. So if I'm asking you to plot, okay, I know what is the loading. Loading is this much. And please show me what the deformed shape will be. We are going to use this function. So at this point, x equals 0, sine pi 0 divided by L will be 0. At this point, L, pi L divided by L is pi, sine pi will be 0. So where is the maximum?
You literally have what I have.
Where is the maximum? The deformed shape. It's going to be deformed shape this way or that way. Where is the maximum? See that here. Right? When x equals to L divided by 2, you get a sine pi divided by 2. Sine pi divided by 2 is 1. So the deformed shape will be like this. And this point is sine pi L x equals to L divided by 2. Right? This is the total length is L.
I did my triangular shape from point 1. So it would tell you the distance from point 1.
Because this is just a deformed shape. I do not tell you what is negative. What is negative? You do not know. You do not know what is the value of C1. Right? So this is one possibility. Another possibility is like this. So this is how buckling happens. When buckling happens, we don't know what is the deformed magnitude. But we don't know what is the shape. The first buckling mode. What about you keep on increasing? What about you keep on increasing the loading? This is the minimum buckling loading, right? What if n equals to 2? Because even you already have buckling, but you do not pay attention, you still keep on increasing the loading. The structure will continue to be deformed. What is that deformed shape? So when n equals to 2, PCR will be n square pi EI. L square equals to 4 pi square EI. This is a critical loading for the second buckling mode occurrence. Because when you keep on increasing the loading, that does not mean after the first buckling loading, you keep on increasing the loading a little bit, you will have the second mode buckling. It's not true. You have to achieve, you have to approach another critical loading to have the second buckling mode. This is the second buckling mode critical loading. N equals to 2, look at this value. This value is 4 times this one. The first buckling load, the first buckling loading is this much. The second one is this much. That means if you want to have higher buckling load, you have to increase the loading significantly, at least 4 times larger than the first one. And then, what is the deformed shape? N square, pi square, L square equals to 4 pi square, L square. And from this, you can derive K equals to 2 pi over L. Then you go back to check what is the shape of the second bucking mode. In homework 5, I'm going to ask you to use ANSYS to plot what is the bucking mode.
Check my code.
In that one, you just click something directly. You do not have to do the calculation. But the first one, the first problem in homework 5 is combination of hand calculation and ANSYS analysis. It's one beam, but I only change the boundary condition.
Or when I
This
put
is the
these
beam,
in,
and that one is one end is fixed. The other one is a pinning joint. So you can follow the same procedure to figure out what is the bucking, critical loading, and also what is the bucking mode. So what is the bucking mode for the second one? Is C1 sine kx over L. Right? K equals to that number.
I might have.
So you will get
okay, I need to do
C1
this when it
sine
looks like that.
2 pi x over L.